Hey, again, we're continuing with section 2.1. We are going to now shift our focus from where we're solving quadratic equations by factorizing to where we're going to solve quadratic equations by completing the square. Now, completing the square is a method that's good to learn for one major reason. Well, really a couple major reasons, but the first and the most important is this. You cannot solve every quadratic equation by factorizing, but you can solve every quadratic equation by completing the square. So it's a method that works 100% of the time, where factorizing, it really truly works for a small percentage of the quadratic equations that are out there. Okay, now the other reason to learn completing the square is it helps us to write equations of certain types of functions and relations in helpful ways, but we'll get to that in other sections. Okay, and before I really talk about what completing the square is, what I really need to talk about with you is how you can solve quadratic equations simply by taking the square roots of both sides of the equation. And this is actually the first way that you would have solved anything quadratic. Take, for instance, the equation that you see right there, x squared is equal to 36. Well, in order to get x by itself, you've been taught that you can take the square root of both sides of the equation, and you make sure you take the positive and negative square root of the side of the equation with the constants, and we're going to get x is equal to plus or minus 6. Now I could have solved that by factoring, set it equal to 0, factor using a difference of squares pattern and so forth, if you follow me, but it was a little bit easier since all I had was a quadratic term and a constant term to go ahead and set x squared equal to the constant and then take the square root of both sides. Okay, now let's see a few more of those. The idea is pretty simple. If I have k squared equals 24, then I'm going to end up taking the square root of both sides, and that will give me k on the left side. I'm going to take the positive and negative square root of the constant. Now 24 is not a perfect square, so I'm going to leave my answer in radical form. Alright, not too difficult to do. And we've talked about simplifying radicals when we were in our prior knowledge section of the course. The square root of 24 is the same thing as the square root of 4 times the square root of 6. I won't continue writing these out throughout the notes, by the way, but I am going to show you this one. And the square root of 4 times the square root of 6 is the same thing as 2 square root of 6. So plus or minus 2 square root of 6. Now, as long as the side of the equation where the variable is located is a perfect square, it's possible to use this method of taking square roots. You see, in this example, I have the difference of c and 3 squared equals 49. Well, since the left side of the equation is a perfect square, right? That's the same thing as if there was an x squared or a k squared there. I can still solve by taking the square roots, and I'm going to show more work than you would have to. The square root of c minus 3 squared would equal plus or minus the square root of 49. And the square root of c minus 3 squared is just c minus 3. And that would give me plus or minus 7. So see, taking the square root of both sides still worked. But there is the additional step of, I don't have c by itself, so I'm going to have to add the 3 to both sides. And then actually this is going to give me two answers here. One answer is that c equals 3 plus 7, which equals 10. And the other answer is going to be c equals 3 minus 7, so c equals negative 4. Alright, let's try one more of those. You go ahead and solve part D for me, please. How'd you do? There you see the simplest form we can give for the exact answers to this particular equation. Alright, the square root of 80 was not a 80 was not a perfect square, so the best we could do with the square root of 80 was to write it as 4 square root of 5. And then if we were going to leave that in radical form, we could not combine it with the negative 5 because they're not like radicals, again, as we studied in the prior knowledge section of our course. And so we can just say this is equal to negative 5 plus or minus 4 square root of 5. And you do have two answers there. You can separate this into where you say one solution is a equals negative 5 plus 4 square root of 5. And then your other solution is a equals negative 5 minus 4 square root of 5. Alright, that 5 is a little off the screen, but you get the idea. Alright, so if you can take the square root of both sides of the equation, it's very easy to solve a quadratic equation. And it is possible to do that with every single quadratic equation, but sometimes there's another additional step that's needed before it's possible to do that. And we want to take a look at what that extra additional step, called completing the square, is all about. We need to pause for a moment and start, I don't mean pause the video, but just pause our thoughts here. And we need to think about what a perfect square trinomial is before I can show you how you can complete a square to solve a quadratic equation. Alright, now let me give you a quick example. You guys know a perfect square is a number that has a square root without decimals or whatever. If I take, for instance, 9 and I square it, I get 81. And then 81 is a perfect square because it could be written as an integer squared, right? It could be written as 9 squared. Well, the same idea works for a perfect square trinomial. A perfect square trinomial is something that you get as a result of squaring a binomial, it turns out. So let's say I had something like a minus 4 squared. Well, if I square a minus 4, that's the same thing as a minus 4 times a minus 4. And that's going to give me a squared. And then it would give me minus 4a 2 times. So you get minus 8a. And then it would give me plus 16. Alright, you can FOIL to check that if you like, but that is a correct square of a minus 4. And that means then that a squared minus 8a plus 16 is a perfect square trinomial because it was a result of squaring a binomial. Okay, so a perfect square trinomial is a result of squaring a binomial. And here is the two common forms of perfect square trinomials. And it's the right side of these equations that I'm going to write down that's going to be relevant. Okay, if you square the sum of two variables, well, it doesn't have to be variables necessarily, you always end up with this. You get the square of the sum of p and q would be p squared plus 2pq plus q squared. Alright, and the second common perfect square trinomial is the square of a difference. If you have the difference of two values and you want to square it, the result of squaring is always going to be that you're going to get p squared minus 2pq plus q squared. Now you're going to see this in practice here right now. I'm going to give you several expressions, and what we're going to do is we're going to fill in the blanks in each of those expressions with a value that would make the expression a perfect square trinomial. And in order to do that, you're going to follow a simple process. Alright, you're going to notice that each of these equations that I'm going to write is going to be written in the standard form for a quadratic equation. This is in the form ax squared, except I didn't use x, I used t. Same thing. Ax squared plus bx plus c. The c is going to be what goes in the blank. The constant term is what we have to figure out in order to make that expression a perfect square trinomial. And what we're going to end up doing to find that value is we're going to use the linear coefficient there. We're going to use the value of b to be able to figure out what the perfect square is. Alright, and it's real simple. The way you find out what the constant term at the end is this. You multiply the value of b by 1/2, and then you square that result. Multiply the value of b by 1/2 and square. Well, half of 16 is 8. 8 squared is 64. And just to show you that's a perfect square trinomial using the patterns that I showed you up here, t squared plus 16t plus 64, well, I could say that I have t squared plus 2 times 8 times t plus 8 squared. So that's like my p squared and my q is equal to 8. So that's like my q squared at the end. And then plus 2pq. P being t and q being 8. Hopefully that makes a little bit of sense. But even if that doesn't make sense, this part can make sense. Let's go on to part B. In order to find what constant value I would add with y squared minus 20y to get a perfect square trinomial, what I'm going to do is I'm going to take half of b, half of the linear coefficient, and square it. Half of negative 20 is negative 10, and if you square negative 10, you get positive 100. That's a perfect square trinomial. Let's try a couple others. Now this next couple are going to be a little bit more difficult simply because b is an odd number instead of an even number, and when you take half of an odd number you don't get an integer. That's fine. I'm just going to have to show you a little extra work for this. We're going to take half of 5 and then we're going to square that value. Alright, watch this up here. We're going to take 1/2 of 5 and then we're going to square that result. And I want you doing this with fractions, not with decimals. Fractions, not with decimals. Not because it's incorrect with decimals, but because you need this practice with fractions, and it's going to make so many problems make more sense if you're able to do this with fractions. Alright, well, half of 5 is 5/2. And then if you square 5/2, you get 25 over 4. So, j squared plus 5j plus 25 over 4 is a perfect square trinomial. I need to go back and do one more thing with each of these later on, I'm realizing. Alright, then x squared minus 11x plus something is going to give us a perfect square trinomial. Figure out what that is for me. Alright, and you can check out my work at the top right part of the screen. I did take half of negative 11 and I squared it and got 121 over 4. Now I mentioned there is something else that I need to go back and teach you about each of these expressions. In order for something to be a perfect square trinomial, it had to be equal to the square of a binomial. And what we didn't do is go back and look and see what binomial would you square to get each of these values. Okay? And I'd like to teach you how you figure out what binomial you squared to get a perfect square trinomial. And simply, the way you're going to do that is this. You're going to take a look at the first term and the last term in the perfect square trinomial, and you're going to take their square roots, 2 and 8 in this case, and then whatever the sign is in front of b, you're going to put that in the middle, and then write it as squared. This is the same thing as t plus 8 squared. Alright, the square root of y squared is y. The square root of 100 is 10. There's a subtraction sign in front of the linear term. That's y minus 10 squared. Okay, this is j plus, and the square root of 25/4 is 5/2 squared. And then this is x minus 11 over 2 squared. Alright, one more example here, then we're ready to solve equations by completing the square. Alright, what if the value of b is already a fraction? Well, you're still going to take half of that value and square it. Try that real quick. Take half of 3/4, leave that result as a fraction, and square it. See what you get for the constant value that will make this a perfect square trinomial. Then see if you can figure out what binomial you can square that would give you that trinomial. There you go. Compare your work with mine as far as what you needed to add to complete that perfect square. And then in terms of what binomial would you square to get that perfect square trinomial, it would be r plus 3/8 squared. Good. Let's put that into practice. Alright, I got two more equations that I want us to solve by taking square roots. And hopefully what you're going to notice here is that in each of these equations, this quantity that I have on the left side is already a perfect square. This is already a perfect square. Now, how do I know that those are already perfect squares? Well, because if I look at x squared minus 16x, and I take half of negative 16, which is negative 8, and square it, I would get 64. If that would have been a blank there, right? If that had been a blank there, you would have said 64 is what you would have added to get a perfect square. Well, alright, and that's what was already there. Same thing here. If this had been a blank where the 49/4 is, well, you would have said half of 7 is 7 halves, and 7 halves squared is 49/4. So that's a perfect square trinomial. And it's really nice when you've got a perfect square trinomial already on the side of the equation where the variables are. Because then all I have to do is figure out, well, what binomial squared gives me that value. And remember, we can figure that out just by taking the square root of the first and last term of the trinomial and putting this sign, whatever that sign happens to be in front of it. We can make that x minus 8 squared is equal to 10. And then, since the left side of the equation is a perfect square, we can take the square root of both sides. We could say x minus 8 equals plus or minus the square root of 10. So x would be equal to 8 plus or minus, or positive 8 plus or minus the square root of 10. Okay, with part B, you would get x plus 7 halves squared equals 25/4. Then take the square root of both sides. X plus 7 halves equals plus or minus, and the square root of 25 is 5, the square root of 4 is 2. So then x would equal negative 7 halves plus or minus 5 halves. Now you notice there's no radicals left in that answer, which means we ought to actually combine those terms then. Negative 7 halves plus 5 halves will get you negative 2 halves, which is negative 1. And then negative 7 halves minus 5 halves would get you negative 12 halves, which is negative 6. Alright, let's take this up to the last step. At least for this video. There is one more video where we're going to make this a little bit more difficult. Got some equations here that we're going to solve by completing the square. This time, though, you're going to notice that this trinomial on the left side of the equation is not a perfect square. If you take half of negative 20 and square it, you don't get 36. Alright, so what happens if you have a non-perfect square on the side of the equation where the variable is? Well, what we're going to do first is we're going to get the constant term on the opposite side of the equation from the linear term and the quadratic term, like that. So subtract 36 from both sides. Then we're going to figure out what would we add to x squared minus 20x that would make a perfect square. Okay, well, you already know that that's going to be 100, because you take half of negative 20 and square it. Now watch what I do right here. I'm going to add that 100 and make a perfect square. But I have to keep in mind that in an equation, whatever I do to change the value of one side of the equation, I have to do the exact same thing to change the value of the other side of the equation. So I also going to need to add 100 to the right side of the equation as well. And now I'm going to have that scenario where I've got a binomial squared, because I can write this as x minus 10 squared on the left side of the equation equals 64. And then I can take the square root of both sides to solve. Alright, and so when we get to x equals 10 plus or minus 8, well, 10 plus 8 is 18, so that's one solution. 10 minus 8 is 2, that's the other solution. Try solving part B on your own right now. It will involve fractions. That's not a problem though. Alright, check your workout with mine. There's a couple of places that we ought to talk about, but if you need to check the work before, while I'm not talking, just pause the video now that the work's on the screen, check your work, and then I'll point out the couple things that I need to highlight. And one of those things is, what did we do when we added -1 with 9/4? Well, hopefully you guys know to get a common denominator anytime you're doing addition of fractions. And so I simply made that -1 into -4/4. And -4/4 plus 9/4 is 5/4, right there. Okay, and then the second thing is, when I took the square root of that fraction, notice that 5 is not a perfect square, and so I just left its square root in radical form. Whereas the denominator 4, it was a perfect square, and so I don't have a radical on the denominator after I took the square root because the square root of 4 is 2. And then finally, because one of the values had a radical in it and the other one didn't, these were not like radicals, and so I couldn't make my answer any simpler than that. There was another way to writing it, but it's not any simpler. There was just a way to write it as one fraction. Okay, that's completing the square. We still need to increase the difficulty of this a little bit, so I'm going to make one more short video. I know this is kind of long. I'm going to make one more short video that talks about completing the square with more difficult situations. Thanks for your attention. Good luck.